Section: Introduction. In this section, we discuss the advancements brought by large language models, LLMs, and the challenges posed by their static training processes, which can lead to outdated knowledge. To tackle this issue, recent research has introduced knowledge editing, K, protocols aimed at updating specific information in the models while keeping unrelated knowledge intact. However, the exact effects of K on models remain unclear. For instance, if we change the fact that Michael Jordan won the 1998 NBA MVP to Reggie Miller won the 1998 NBA MVP, we question what other beliefs the model might adopt. Should it forget that Michael Jordan and the Chicago Bulls reached the finals that year? Should it mistakenly think Reggie Miller played for the Bulls? These questions highlight the complexity of understanding K's impact. Motivated by these uncertainties, we aim to explore how K affects a model's internal representations. We propose two main tasks. First, to identify how a model represents knowledge about specific entities, and second, to examine how these representations change when we apply K. Instead of analyzing a complex LLM directly, we draw inspiration from recent studies that create simplified models to test our hypotheses. We establish a structured knowledge graph where entities are connected through defined relationships, forming a broader structure. By training a transformer on sequences derived from this graph, we find that the model accurately captures its structure. However, when we apply K to modify facts or introduce counterfactuals, we observe a significant distortion in the model's representations, which we term representation shattering. This distortion correlates with how drastically an edit alters the graph's structure. We hypothesize that representation shattering explains the negative effects of K on a model's factual and reasoning abilities. Our contributions include using structured knowledge graphs to investigate K's impact, demonstrating that K can disrupt the global structure of the model's representations, and providing evidence of representation shattering through experiments with a pre-trained GPT-2 XL model. While our findings are primarily based on synthetic settings, we believe they may extend to more complex scenarios, as suggested by our initial tests with GPT-2 XL. Section Summary. In this section, we explore the challenges of knowledge editing, K, in large language models, highlighting how it can lead to representation shattering, where the model's latent representations are distorted, negatively impacting its factual and reasoning capabilities. We propose using structured knowledge graphs to investigate these effects mechanistically, demonstrating that the extent of harm correlates with the degree of change made during editing. Section: Related work. In this section, we discuss related work on knowledge editing, K. We note that various protocols for KE have been introduced recently. Early research focused on meta-learning approaches and outlined the essential properties that a KE protocol should meet, such as ensuring that unrelated facts remain unaffected by the editing process. Building on studies that explore how transformers store knowledge, current K protocols aim to define specific operations that target knowledge within certain model components, like MLP layers, and modify factual associations by assuming that knowledge is stored in a localized way. We recognize that the K problem is not well defined, making it difficult to predict how edits to knowledge will impact other facts learned during training. Previous studies have taken a different route, concentrating on understanding the effects of K protocols empirically. For instance, they examine how edits influence counterfactual statements or unrelated facts. These studies generally reveal that K can severely harm a model's overall knowledge and reasoning skills. While most of this research relies on empirical benchmarking of edited models, we choose to conduct a mechanistic analysis to understand how editing changes a model's representations, even if we use simplified tasks. To better understand the shortcomings of K methods, we advocate for a more controlled and interpretable experimental setup. This approach allows us to formulate specific hypotheses about why K negatively impacts models, which we can then test in more realistic scenarios through carefully designed experiments. Our methodology of using simplified tasks to explore neural network behavior has yielded valuable insights in recent years, such as how chain-of-thought reasoning enhances model capabilities and the existence of nonlinear representations. We also address the concept of knowledge editing through a structured definition based on knowledge graphs. These graphs illustrate how facts, entities, and relationships are interconnected, leading to ideas of consistency and reasoning across information. We will establish a synthetic data generation process using knowledge graphs to systematically investigate K in transformers. A knowledge graph consists of a set of entities and a collection of facts that connect these entities. For example, a graph with entities like Alice, Bob, and Carol can represent the fact that Alice is the advisor of Bob, using the relationship advisor. Formally, a knowledge graph includes nodes, relations, and facts, where each fact is defined by a relationship between two entities. A subgraph can be created by focusing on facts that involve a specific relationship, such as all facts related to advisor. Knowledge graphs also allow us to infer related facts. For instance, from the facts, Alice's advisor was Bob, and Bob's advisor was Carol, we can derive the statement, Alice's advisor's advisor was Carol. To capture these connections, we define compositions of relations, which are crucial for understanding the ripple effects that occur in the graph after an edit. A composition of relations involves a sequence of relationships that connect facts within the knowledge graph, ensuring that any fact defined by this composition corresponds to a set of related facts. Section Summary. In this section, we review various knowledge editing (K) protocols, highlighting their focus on localized knowledge manipulation within models and the detrimental effects these edits can have on a model's overall reasoning and knowledge retention. We also propose using structured knowledge graphs to systematically study K, defining key concepts such as relations and compositions of relations to understand the ripple effects of edits within the graph. Section: Cyclic graphs, a description of the entities and relations. In this section, we explore knowledge graphs where each relation subgraph consists of separate cyclic graphs. For every entity, there is exactly one other entity connected by a specific relation. We choose a cyclic structure as a key feature because cycles frequently appear in natural language contexts. For instance, we illustrate how representations of months and days naturally form cycles. Our knowledge editing methods focus on a set of entities where we want to change specific facts while keeping other related facts intact. We evaluate our methods using a test set of facts. The knowledge graph we define includes 3 relations and 2048 entities, organized into 3 distinct cyclic orders. When we edit knowledge, we identify the cyclic order containing the fact we want to change as the edit subgraph. We then randomly select one of the other 2 cyclic orders as the retained subgraph to sample facts from, while the last order serves as the test subgraph for evaluation. We create 8 relations for each cyclic order, resulting in a total of 24 relations. These relations correspond to neighboring entities in both clockwise and counterclockwise directions. We utilize a method called roam for our analysis, specifically targeting the relations in the edit subgraph. We test the edited facts to see if the changes were successful, while the retained subgraph helps minimize unintended changes to unrelated facts. The test subgraph remains untouched and is used to check if unrelated facts stay the same after edits. The one-hop neighbor relations form a single cycle, while 2-hop relations consist of 2 cycles, and so on. Each k-hop relation is interconnected, meaning any change to one should align with the others. An edit involves altering a fact in the knowledge graph, which can also be seen as changing a connection in the relation graph. We define the distance of an edit as the shortest path between the original and modified entities in the cyclic order. For our data generation process, we create a sequence of alternating entities and relations. Each triplet of entity, relation, and entity forms a fact in the knowledge graph. We sample each token uniformly from all possible options. For example, a sequence might look like 1i_C433_A273_A322_C26, representing alternating entities and relations. This sampling mimics random walks on the knowledge graph. In our training setup, we train a transformer model using next token prediction on the synthetic data generated earlier. We use a two-layer nano-GPT transformer for all experiments. For evaluation, we check the model's ability to recall facts it has seen during training, both before and after any edits. We prompt the model with an entity and a relation, expecting it to produce the corresponding entity as the next token. Section Summary. In this section, we study knowledge graphs composed of disjoint cyclic graphs, where each entity is linked to exactly one other entity through defined relations. We implement a knowledge editing method using a cyclic structure to ensure that edits to specific facts do not alter unrelated relations, and we evaluate the model's ability to recall facts before and after these edits. Section: Evaluation, Unseen Facts. In this section, we evaluate our model based on two additional criteria. First, we assess compositional inference, which involves testing the model on combinations of relations beyond those seen during training. The model needs to maintain the geometric structure of the data to generalize effectively after we edit knowledge. Second, we look at logical inference, a crucial aspect of reasoning in natural language. For instance, if we know Alice advises Bob, we can logically conclude that Bob is Alice's advisee, even if this isn't directly stated. Our data generation includes similar relationships, like clockwise and anti-clockwise neighbors. By intentionally leaving out one direction in some relation pairs during training, we can evaluate how well the model understands the connections between related relations. We also check if changing a fact for one relation affects other related facts, ensuring the model's knowledge remains logically consistent after edits. Next, we explore Rank 1 model editing, ROME, a typical knowledge editing algorithm for language models. We perform two types of edits: corrective edits, which fix facts the model remembers incorrectly, and counterfactual edits, which change a fact to introduce a new one, creating inconsistencies in the knowledge graph. Our findings indicate that representation shattering can explain the decline in model performance after knowledge editing. We evaluate the impact of these edits in three ways. First, we measure direct recall accuracy for facts seen during training. Second, we assess logical inference accuracy on a subset of relations that can be inferred from others. Third, we look at compositional inference accuracy for combinations of two relations. Both logical and compositional inference accuracy focus on samples that are outside the training distribution. Since our models are trained on a mix of facts, multiple prompts can lead to the same fact. To account for this, we sample three sequences that elicit the same fact and average the output probabilities. We report scores for all three metrics based on cyclic orders. Before knowledge editing, the model's logical and compositional inference accuracies are close to direct recall accuracy, indicating good generalization. However, after knowledge editing, all accuracies drop, especially for counterfactual edits, which create inconsistencies. The accuracies remain similar across all relations, regardless of their cyclic order, allowing us to interchangeably compute accuracy. We find that transformer representations effectively capture the data's geometry. The model shows high compositional and logical inference accuracies before knowledge editing, suggesting it understands the overall structure rather than just memorizing facts. We visualize this using isomap, a method for reducing dimensions based on local neighborhood graphs. We plot the evolution of the internal representation during training, showing how different entity values relate to a fixed relation, colored by cyclic ordering. The representation manifold reflects the cyclic ordering of entities, especially towards the end of training. When we apply corrective knowledge edits, we observe that the representation changes unexpectedly. Instead of improving performance, these edits lead to a decline in all accuracies. This aligns with previous findings that show reasoning capabilities can worsen after corrective edits. We visualize the representations of three models, each resulting from different edits, selected for their varying direct recall accuracies. We notice that the model with the highest accuracy maintains the data's geometric structure after the edit, while lower accuracy models show more distortion, failing to capture the data's geometry. We term this loss of structure as representation shattering, which can result from knowledge editing. We also measure the extent of shattering using the Frobenius norm of the change in the distance matrix before and after the edit, finding that larger changes correlate with greater drops in performance across all accuracy measures. Section Summary. In this section, we evaluate our model's performance on compositional and logical inference after knowledge editing, finding that while it initially generalizes well, both types of edits lead to a significant drop in accuracy, particularly for counterfactual edits. We also observe that corrective edits can distort the model's internal representation, a phenomenon we term representation shattering, which negatively impacts reasoning capabilities. Section. How do different counterfactual edits change the extent of shattering? In this section, we explore how different counterfactual edits affect the degree of shattering. Counterfactual editing is a method we use to evaluate knowledge extraction by introducing new facts that were not seen during training. We examine 25 distinct counterfactual edits, each corresponding to a specific counterfactual edit distance, which measures how far apart the old fact and the new fact are in a cyclic order. For instance, we illustrate a case where the edit distance is 1. Our findings indicate that as we increase the distance of the counterfactual edit, accuracy decreases while the extent of shattering increases. This means that when we change one entity to another, the further apart they are, the more shattering occurs. For example, changing December to November yields higher accuracy than changing it to July. From these observations, we propose the following hypothesis. Language models represent related entities in a structured way, and knowledge extraction methods disrupt this structure to add or modify facts, leading to representation shattering. The degree of this shattering grows with the distance between the old and new facts. Next, we investigate whether our results apply to large transformers trained on real-world data. We focus on concepts with a cyclic order, specifically the months of the year, and apply counterfactual edits to GPT-2 using Rome to rearrange the months. We create prompts like, 1 month after January is February, and modify the answers based on the edit distance. For a distance of 1, we change the answer to March, and for a distance of 2, to April, and so forth. After updating GPT-2 with these new prompt answer pairs, we analyze the latent embeddings for the months before and after the edits. We observe that as we increase the edit distance from 1 to 5, the representation shattering also increases. Finally, we assess how this representation shattering impacts the model's performance. We evaluate GPT-2 on a reasoning task before and after the edits. As the edit distance rises, we notice a gradual decline in accuracy, with a significant drop at a distance of 4, which aligns with the point of representation shattering. This indicates that our findings from synthetic data are applicable to larger models trained on real-world data.